So we are starting our last unit. It's divided into two pieces. We're going to start with differential equations, and then we'll talk about parametric, polar, and conic sections. So differential equations, we're just giving you a little intro to it. A lot of you will probably take an entire class on differential equations. So we need to start by learning the vocabulary. We will then be able to determine if a function is a solution to a given differential equation. Given a general solution, we'll be able to determine a particular solution given a condition that we need to fulfill. And we're going to talk about logistic growth models, when they're increasing, decreasing, and when they're at equilibrium. So first thing, there's our goals, we need is to know what a differential equation is. And a differential equation is just an equation with a derivative in it. The differential equation has a derivative in it. Our goal is not to find just a number for an answer, but a function. The solution is a function. So, some examples. dy dx plus 4y equals cosine of x. That's a differential equation. Second derivative plus 16y equals 0. That's a differential equation. And the last one, another differential equation, just with primed notation instead of Leibniz notation. The first one, A and C, are both first-order differential equations, whereas B is a second-order differential equation because the order is the highest order derivative that appears in the equation. So, order of a differential equation is the highest derivative in it. Linear versus nonlinear. A differential equation is linear if y and its derivative are only to the first power. They're not composed with other functions. A linear equation cannot have products or quotients of y or its derivative. So they're simpler. Linear differential equations. Y and its derivatives are to the first power. They're not multiplied together or they're composed with other functions. The first power, not composed with other functions, and they cannot have products or quotients of y's and its derivative. So, no products or quotients. If any of those things happen, then it's a nonlinear differential equation. Now, let's look at some examples. Example 1, let's start with the easy thing, the order. Turn this light off so that gets rid of that glare. There, that's better. So, we'll start with the order because it's easy to look at it and see what the highest derivative is. We have A, B, C, D, and E. A has a first derivative, so it's a first order differential equation. B has a second derivative. It's a second order. C again has a first derivative. D has a second derivative and a first derivative, so it gets to be second because that's the biggest. And then E has a third derivative because when you have a little 3 inside parentheses, that means the third derivative. It doesn't mean y to the third power. Now, linear versus nonlinear. So, the first one there, we have y primed. It's not raised to a power. It's not composed with another function. It's not a product or in a quotient with y or any of its derivatives. So this one's linear. B, we have a second derivative. It's not raised to a power. It's not multiplied by y or any other derivative, and it's not the object of a function. It's not composed with anything, and neither is y. So this one's also linear. It's okay to divide it by x squared plus 1. That doesn't make it nonlinear. If it were divided by y squared plus 1, that would make it nonlinear. Like C is not linear because you have 1 over y. So this one's nonlinear. D, again, y prime, second derivative, it's okay. You can multiply the derivative by 2, you just can't multiply it by something with a y in it. 3, you can multiply y by that, and then the rest just has x's in it. So this one's linear. And finally, the third derivative is equal to 2, that's linear. Now, I'm asking you these questions. This isn't the type of thing you're going to be tested on. It's just good to be able to recognize them so you'll know which method to use to solve them. And there's the pretty answers. So, one of the first types we're going to learn are separable differential equations. So most general first-order differential equation can be written as y primed is equal to some function of f, t, and y, and you can rewrite it so that you separate all the y's from all of the variables, in this case t. So, separable differential equation. Can write the equation with y's on one side of the equal and the other variable on the other. That's what all those words are saying. So the terms that involve y appear on one side. They're separated from the terms that involve the variable. Lots of definitions in this section. Don't be overwhelmed. The general solution is a family of solutions, actually, just like with integrals. Your first solution had the plus c in it. That's the general solution of a differential equation. Is going to have some arbitrary constants in it. So your general solution contains constants. And then a initial value problem gives you some conditions, and I just call it IVP, initial value problem. Gives you a initial condition that will allow you to figure out what those constants are. So an initial value problem consists of a condition and a differential equation. Condition. Let's get rid of that. Consists of condition and a differential equation. And you solved these back in Calc 1 when you were first learning about integrals. We talked about velocity and acceleration, and you would figure out the velocity given the acceleration and the initial velocity, and then you could figure out the position function given the initial position and the velocity function. Those were initial value problems. You've done these already. Okay. Let's look at a differential equation. Consider the population of field mice on a secluded island. In the absence of predators, the population growth rate will be proportional to its size. So proportional means you can multiply it by some proportionality constant. Write this as an equation if the population size is given by P of t and the constant of proportionality is 0.5. So we're going to write an initial value problem. Actually, so far it's not an initial value problem. We don't have an initial value yet. We just know that its population growth rate is proportional to its size. So dp dt is equal to some proportionality constant, and it was really nice, they gave it to us, times p. That's all we can do. Show that p of t equals 500 e to the 0.5 t is a solution. Okay. So that was one of our goals, was to be able to show that a given equation, a given function, is a solution to a differential equation. So we want to show that it solves this differential equation. So first thing I do is take the derivative of that thing. So I have 500 and then e to the 0.5 t. So the derivative of e to the 0.5 t is e to the 0.5 t times 0.5, because that's the chain rule. Well, that's just equal to 0.5. This is the p that we started with. So we have shown that it is a solution to our equation. Show that p of t equals c e to the 0.5 t is a solution. So starting with p equals c times e to the 0.5 t, I have c e to the 0.5 t times the derivative of 0.5 t, which is 0.5, which happens to be equal to 0.5 times my p. This is a general solution. It has a constant in it. This one is a particular solution, or a specific solution. Usually you get your particular or specific solution from the initial value. So here's the pretty solutions. So, solutions like the one in part C that depend on one or more constant are called general solutions. Since the constant comes from integration, most solutions will have at least one. And then we have to have something else that we know that helps us to come up with our particular or specific solution. If the population of field mice in the prior example is estimated to be 1,000 mice at time t equals 0, find the specific solution given the general solution from part C. So, example 5, we have our initial value problem was that P at time 0 is equal to 1,000, and dp dt is equal to 0.5 times p. This is an initial value problem. My general solution, which you will figure out how to calculate really soon, to this initial value problem is P of t is equal to some constant e to the 0.5 t. Then we use our initial value, P of 0 equals c times e to the 0.5 times 0 has to be equal to 1,000. But e to the 0 power is just 1, so c equals 1,000. So P of t is equal to 1,000 e to the 0.5 t. One model of growth of a population is just based on the assumption that the population grows at a rate proportional to the size of the population, just like our field mice did in the example we looked at. And that's reasonable, assuming that there's enough room and enough food and resources and no predators. In that case, then we let t, time, be the independent variable, p, the population. Then the derivative of p with respect to time is equal to k times p. This is natural growth. And it ends up being exponential growth. Natural growth model where dp dt is equal to some constant k, proportionality constant, times the population. Okay, if we look at this model and we just don't consider models with no population, because that would be boring. If the population is positive and k is positive, then the derivative will be positive. That means the population is always increasing as long as the population is positive and the proportionality constant is positive. So the derivative will be increasing. The growth rate increases as the population increases. Okay, so you want to think about a solution to this. This says that a function whose derivative is a constant multiple of itself. Well, that's the exponential function. So that's why we end up with c times e to the kt as the general solution for that problem. And we will show you how to solve that differential equation in the next couple of sections. And because we don't really go back in time and we don't have negative populations, we can really just look at it there in quadrant 1. Many populations start out growing that way, but then they reach a point where they have to start leveling off. So we want to take into account that there's some carrying capacity, M, which is the biggest number of mice that could actually fit on the island. So for a model that takes into account both trends, that it grows really fast at the beginning, but then as it approaches that carrying capacity, its growth rate slows down. So the derivative is small when you're getting close to the carrying capacity, and it's large when you're just getting started. It's positive when you're below that carrying capacity, but if you somehow jump up above the carrying capacity, the derivative would need to be negative. And this is the model that does that. So this one is logistic growth model. So the derivative of the population with respect to time is equal to some proportionality constant times the population times 1 minus the proportion of the population and the carrying capacity. M equals carrying capacity, or max population. So, if P is small compared with M, so you don't have a whole lot of population yet, then this would be a really small thing that you're subtracting from 1. So your growth rate would be pretty much just dependent upon P. If your carrying capacity is getting really close to your population, then this would be getting close to 1. You would be multiplying P by something very small, so your growth rate would be getting very small. Now, you have constant functions when the population is equal to 0 and the population are equal to M. So, if P equals 0 or P equals M, P equals 0, derivative is equal to 0. If P equals M, then you have M over M, so the derivative is equal to 0. Then dP dt is equal to 0. These are equilibrium solutions. There's no impetus for them to change. Nothing is trying to make them grow or shrink. They're just going to sit there because their growth rate is 0. So if the population, initial population, lies between 0 to M, then the right side of this equation is positive. So your derivative, let's see, between 0 and M. Okay, so then this would be positive, so you're growing. If P is greater than M, then P over M would be bigger than 1, and you would be decreasing. Either way, your population is trying its best to get there to M. It looks something like this. So, let's look at a practice. We have dP dt is equal to 1.2 times P 1 minus P over 4,200. So, that means that M, carrying capacity, is 4,200. For what values of P is the population increasing? Well, as soon as population gets bigger than 0, it's increasing. And it's going to keep increasing until it gets to 4,200. At 4,200, you would have 4,200 over 4,200, and it would stop growing. If P is bigger than 4,200, then you would have something bigger than 1 here, so you would have 1 minus something bigger than 1, so your derivative would be negative. So your population is decreasing when it gets above 4,200. And the equilibrium solutions are 0 and 4,200. Yeah, it's that easy. Okay, so let's talk about general differential equations again. We consider the differential equation y primed equals x times y. It's understood that y is a function with x's in it. A function f is called a solution to the differential equation if it satisfies that equation. So we need to be able to check and be sure that a given function is the solution to a differential equation. You're going to be asked to solve them later, but right now we just want to be able to show that something is a solution. So let's look at an example of that. Show that every member of the family of functions y equals 1 plus c e to the t over 1 minus c e to the t is a solution to the differential equation y primed equals 1/2 of y squared minus 1. So you want to confirm this. Make sure that this is true for this particular function. First thing I would do is take the derivative and see what it looks like. So y primed is equal to low d high less high d low all over low times low. So I'm going to do some simplifying and then I'll get back to you. Well, I distributed and I ended up with a minus c squared e to the 2t and a plus c squared e to the 2t. I ended up with just 2c e to the t over 1 minus c e to the t squared. That does not jump out at me as being 1/2 of y squared minus 1. So let's look at 1/2 of y squared minus 1. So this is the left-hand side. So 1/2 of 1 plus c e to the t over 1 plus minus c e to the t. Go ahead and give that a big set of parentheses. 1 minus c e to the t squared minus 1. So I'm going to square stuff and get a least common denominator, and I'll meet you back here again. Okay, I made some progress. I squared 1 plus c e to the t. I squared 1 minus c e to the t. And then I knew I had to write 1 as this denominator over that denominator. You know, same thing. So then I rewrote them in one handy unit. I made sure I distributed that minus sign, so the 1 became minus, that became a plus, that became a minus. And then I just put that back as 1 minus c e to the t power. So now 1 goes away, c squared e to the 2t goes away. I have 1/2 of 4c e to the t, because I have 2c e to the t, 2c e to the t, over 1 minus c e to the t squared. That 2 goes into 4, leaves me with 2c e to the t over 1 minus c e to the t squared, which, oh, look at that. That's equal to y primed, which is exactly what I wanted to show. So yes, so we want to find a solution of the differential equation y primed equals 1/2 of y squared minus 1 that satisfies the differential equation y of 0 equals 2. So we know what it looks like. Luckily, we don't have to solve this equation because we don't know how to do that yet. But we do know that our general solution looks like this. So y equals 1 plus c e to the t over 1 minus c e to the t is our general solution. And y of 0 equals 2 is our initial condition. So we just have to figure out what c makes this true. So 2 has to be equal to 1 plus c e to the 0 over 1 minus c e to the 0. I put zeros in for t. I put 2 in for y. So 2 times 1 minus c e to the 0 equals 1 plus c e to the 0. And I don't know why I'm writing down e to the 0, because I know that e to the 0 is equal to 1. So 2 times 1 minus c is equal to 1 plus c. So 2 minus 2c is 1 plus c. So let's get everything with c's over on the right-hand side. So 2 minus 1 is 1. And that's equal to 3c. So c is equal to 1/3. So y is equal to 1 plus 1/3 e to the t over 1 minus 1/3 e to the t. Okay, so practice problem, initial value problem. First, verify that negative t cosine t minus t is a solution to that differential equation, and then verify that if you plug pi in, 0 comes out. So give it a try. We'll meet back here and compare answers. So I wrote down the problem. I took the derivative. It was a product rule, so derivative of negative t times cosine, negative t times the derivative of cosine minus the derivative of negative t. So then I just kind of did a minus minus and made it a plus. Then I took t times dy dt because I was trying to make it look like the differential equation here. So t times dy dt, I distributed. Then I just kind of rearranged, made this look exactly like y plus 2t squared t, which is exactly what we wanted. I had run out of room, so I came up here. I plugged in negative pi, I plugged in pi, excuse me. That gave me minus pi cosine pi minus pi. So that's minus pi, cosine of pi is -1, pi minus pi is 0, which is exactly what we wanted it to be. Example 6. We want to verify that e to the arctan of x times c is a general solution to the differential equation y primed equals y over x squared plus 1, and then use that point to find a specific solution. So another initial value problem. I know the answer sitting right there, but I wrote it out too. So first thing I did was I took the derivative. The derivative of c times e to the arctan of x. Well, derivative of e raised to something is e raised to something times the derivative of the exponent. Derivative of arctan is 1 over 1 plus x squared. But c e to the arctan happens to be y, so y primed is y over 1 plus x squared. Easy enough. So now I plug 0 in, and I want pi to come out. So pi needs to be equal to c times the arctan of 0. Arctan of 0 is 0. E to the 0 is 1, so c is just pi. That one's pretty easy. Now, let's look at example 7. We want to find the general solution and then use the general solution and the fact that y primed at 0 is 5 and y at pi is equal to 3 to find a specific solution that meets these conditions. So I did it once and I just kind of went directly to B. So let's look at just part A where I find the general solution. There it is. So 7a, we have the second derivative is equal to 3x plus sine of x. So first thing I do is I take the integral because that will give me the first derivative. And the first derivative has a constant in it. I named that constant c. I want to know what y is, so I take the integral of the first derivative. I need another constant for that. So I have 3x squared over 2 minus sine of x, because the antiderivative of sine was minus cosine. Antiderivative of minus cosine is minus sine. The others are just add 1 to the exponent, divide by the new exponent. Then I end up with y equals 3x squared minus sine x plus cx plus d. And then for b, use your general solution and those initial conditions to find a specific solution. So I look at the derivative. You have to work backwards, go from the derivative and then back to the original function. So first thing I do is I plug 0 into that derivative and make sure 5 comes out. So 0 times 3 is 0. Cosine of 0 is 1, so it's minus 1 plus c. C has to be equal to 6. Then I plug that into c for my y function, and I plug pi in, and 3 has to come out, and that one didn't come out nearly as pretty because I end up with 3 pi squared over 2 minus sine of pi plus 6 pi plus d, and then I solved for d. Luckily, sine of pi was equal to 0, so that made it slightly simpler, but I still ended up with a pretty complicated constant. So my function is equal to 3x squared over 2 minus sine x plus 6x plus d, which is this constant. I'm going to pause and we'll look at example 8. So example 8 doesn't give us our differential equation. We're going to have to come up with it on our own. A canister is dropped from a helicopter 500 meters above the ground. Its parachute does not open, but the canister has been designed to withstand an impact speed of 100 meters per second. Will it survive the impact or will it burst? And we need to justify our answer. So step number 1 is just finding out how can we answer the question. So example 8, we need to know the velocity at the moment of impact. Well, in order to find that, we're going to need 1, a velocity function, and 2, we need to know when the moment of impact is. So we need a function. We need some function, and let's name it h of t, which is equal to the height of the canister. So, what do we know about the height of the canister? Well, we know at time 0 is 500 meters. Do we know anything about h primed? Remember, h primed would be equal to the velocity of the canister. Well, we need a function for that. We don't know that yet. But we do know that the acceleration due to gravity is 9.8 meters per second squared. So acceleration is equal to the second derivative of the height function is equal to negative 9.8 meters per second squared. So we're making progress. Now, I have an initial height. Do I have an initial velocity? Well, it says that the canister is dropped. It's just dropped. It's not thrown. So velocity at time 0 is equal to 0. So here's my initial value problem. I have h of 0, is equal to 500. H primed of 0 is equal to 0. And the second derivative at any time is equal to negative 9.8. So there's my initial value problem. H primed of t is equal to the integral of negative 9.8 dt. So that would be negative 9.8 t plus a constant. But I know that the velocity, or the derivative of height, at time 0 is 0. So h primed of 0 equals negative 9.8 times 0 plus c needs to be equal to 0. So that constant is just equal to 0. So now we'll look at, that's h primed of t. H of t is going to be the integral of negative 9.8 t dt. So that's add 1 to the exponent, divide by the new exponent, plus a constant. So negative 4.9 t squared plus a constant. And we know the height at time 0 is equal to 500 which is negative 4.9 times 0 squared, plus a constant. My constant's 500. So I have a height function. Height at any time is equal to negative 4.9 t squared plus 500. Now let's go back and see if I have what I need to answer my question. I have a velocity function, and I have a height function that I can use to determine the moment of impact. So to determine the moment of impact, I take h of t, negative 4.9 t plus 500 t squared, and set that equal to 0. So 4.9 t squared is equal to 500, so t squared is 500 over 4.9. So t is plus or minus the square root of that. And since I've already done this problem because Yuja froze up on me and I had to redo it, I already know that the answer to that is 10.10. So it takes about 10.10 seconds for the canister to hit the ground. So I want to find the velocity at that time, which is h primed of t. So negative 9.8 times 10.10 gives me negative 98.99 meters per second. So if their testing is accurate, then it should survive the impact. There you go. We're going to do lots more fun problems with differential equations.